Hello, my name is Dibyendu Nandi. I am a professor at the Center for Excellence in Space Sciences, India, and the Department of Physical Sciences at IISER, Kolkata. My specialty is astrophysical magnetic fields, specifically focusing on the Sun. I will be giving you a series of lectures on the Sun, which will cover various aspects of solar activity. So, what I will do is first motivate why it is important to understand the Sun and its activity, and subsequently I will go on to describe various observational aspects and theoretical underpinnings which help us understand the Sun. So, why is it important to understand the Sun? So, the Sun is our nearest star and this sustains life on Earth. The energy that the Sun generates drives climate and atmospheric processes on the Earth and other planets. And the Sun is not a constant star, it's variable, its activity levels vary, and this variable activity governs the electromagnetic and particulate environment of the solar system and has important consequences for the variation of the near Earth space environment to which our space based technologies such as satellites are subject to. And so, it is important to be able to understand the activity and the variability of the Sun, so that we are able to assess its impact on our space based technologies. And also on the larger perspective, the Sun provides a window to exploring other similar stars in the universe, because we can make high spatial resolution observations of the Sun, which is otherwise not possible for any other star, and to understand various plasma processes and stellar processes. We can use the Sun as a laboratory to develop our understanding of other stars. So, here is the outline of the different modules which are going to be part of my lecture on the Sun. So, in the first module I will talk about the introduction to the Sun as a star, where I will talk about the evolution of the Sun and what holds it together during its main sequence lifetime and what is going to be its ultimate fate. So, this is more sort of putting the Sun in the context of stellar evolution, which I think is important to keep in the back of your mind when you study the Sun. In the second module, we will go through observations of various stellar activity phenomena and with a specific focus on the magnetic activity of the Sun. In the third module, we will discuss the theoretical underpinnings of magnetohydrodynamics, which is the subject that is necessary to understand how the Sun produces magnetically mediated activity. In the fourth module, we will focus on the solar dynamo mechanism, which produces magnetic activity of the Sun and also other stars. In the fifth module, we will discuss solar influences on the space environment, which is known as space weather and planetary climates, and in the sixth module, we will discuss Sun planet interactions and what these interactions imply for habitability and life. So, let us begin with module 1, which is an introduction to the Sun as a star. So, if you look at the current Sun and its physical properties, the Sun is a sort of a normal star with a mass of about 2 × 10⁻30 kilograms, and it has a radius of about 7 × 10⁸ meters and a surface temperature of about 6000 degrees Kelvin. Now, this kind of a mass and radius and the surface temperature puts this in a sort of a stellar classification type of G2, which is often referred to as a yellow dwarf, and to be precise, it is a G2V star. And in the overall context of stellar activity, the Sun's activity levels are moderate to weak. So, it is not necessarily a very active star, it is sort of moderately weak activity level star. So, the question is how did the Sun come to be, how did it originate, and where is it going to go? This is a perspective that we'll keep in mind, although eventually in the other modules we'll focus on the activity of the current sun. Here in this module we'll look at the sun in the context of astrophysics and stellar evolution. So stars like the sun are born through the collapse, gravitational collapse of certain parts or regions of molecular clouds, and what you see here in this image is HST, Hubble Space Telescope image of the Large Magellanic Cloud, and you see that there is a distribution of diffused gas in space, and this region is interspersed with very bright regions which are star forming regions and very bright stars. So essentially what happens is in some regions, due to fluctuations, the gravitational forces, we know what the forces of thermal pressure, which sort of then pulls together material and slowly starts forming a larger body which has a denser region in it, so high density region, and eventually conglomeration of more and more stuff leads to a gravitational collapse, where you end up having a very dense core in the center of this collapsing region in the molecular cloud. And when this region is collapsing, what happens is the pressure and the temperature rises, and eventually the mass is just right, then nuclear reactions are initiated in this core of this stellar, in this collapsing object, which then holds this sort of object together. This is the kind of initial phase of a star. This phase is known as the protostar phase, the pre-main sequence evolution, where based on how much mass was available for this protostar, one can have different trajectories in the main sequence. For the sun, eventually the amount of material that was available could collapse and produce a solar mass like star, where eventually nuclear fusion reaction ignited based on the rising temperatures and pressure, which results in the conversion of hydrogen to helium in the core of a sun. So, in a sun-like star, then the excess pressure which is generated due to the nuclear fusion holds the star together against further gravitational collapse, and when this occurs, a stable star is born, and the star sort of enters the main sequence phase and lives in the main sequence phase for typically on the order of 10 billion years. Okay. So, once the nuclear fuel is over, when there is no more hydrogen left in the core of a sun-like star to sustain the burning of hydrogen to produce helium, there is a series of steps which is initiated, where the sun evolves out from a typical solar-like star to a much larger red giant, and from there eventually it evolves through the phase of a planetary nebula to a white dwarf, which is really a dead star where there is no more nuclear energy generation going on. So, let us briefly sort of go through these various steps of stellar evolution to see what is the ultimate fate of the sun. Before we get there, it will be good for us to kind of have a look at stellar nucleosynthesis and to begin this process with an understanding of the overall perspective of how different elements come into being. So, if you consider the universe, the most abundant element in the universe is hydrogen, which is 71% by mass, followed by helium. The hydrogen atom is the simplest atom to put together, so it is not surprising that it is the most abundant element in the universe. And the sun in fact contains about 75% by mass of hydrogen, and as we discussed, the nucleosynthesis, or the conversion or generation of new nuclear elements through nuclear reactions, occurs in the core of the sun, where hydrogen is fused to form helium. So, helium is the second most abundant element in the sun. Now, if you look at other objects in the universe, for example, planet, and let us take the example of the Earth's crust. We have oxygen, which is very important for us, which is 46% by mass, and then other elements such as silicon, aluminum, iron, carbon, which are higher mass elements, which are also in fact formed in different astrophysical processes. If you look at the Earth's atmosphere, there is nitrogen, there is oxygen, there is water, but not enough hydrogen. And the reason that there isn't enough hydrogen is because there is not enough mass in the Earth. The gravity is not strong enough to hold on to hydrogen, which is very light. That is one reason. And the other reason is the presence of oxygen helps in converting or oxidizing hydrogen to water very efficiently. And of course, water is a very important element for life itself. And if you look at the human body, then we have oxygen, which is again dominant element in the human body. Then we have carbon, we have hydrogen, we have nitrogen, and although we will not be going into the details of this, it turns out that most of these elements which are actually in the human body are produced in different astrophysical context, in different astrophysical processes. So, if we focus on the sun, particularly the primary nuclear reaction that occurs in the sun is the proton-proton chain, which converts hydrogen through a few steps to helium 4, which is a stable isotope of helium. So, first deuterium is produced by combining two hydrogen, and subsequently from there in the next step in the pp chain, helium 4 is produced, and the mass deficit at the end of all of the steps of reactions is what is converted to energy, and this is what drives the activity of a sun-like star. And this reaction is in fact something that is prevalent in solar-like stars. This reaction is also relatively slow because it involves weak interactions, and the nuclear cross section is also relatively small, and the consequences for the reaction rate to be slow, which are in fact important in the overall context of the evolution of the sun and also planets and their habitability. A typical star like the sun has enough hydrogen to last in the main sequence phase for close to something like 10 billion years, and this is determined by the amount of hydrogen that there is in its interior. And the fact that it is not burnt very quickly, but is converted to helium through a very slow nuclear burning is important in the sense that this long time scale that then becomes available for the sun to be in the main sequence also allows for planetary evolution, the evolution of atmospheres, and in fact the evolution of life from primordial life forms to intelligent beings, which sort of happens contemporarily with the evolution of the star. The similarity in time scale of the energy generation process, the necessary conditions that is required in the host star and a planet is something that is very important for the emergence of life. But eventually the sun is going to run out of hydrogen fuel, and this will sort of herald the next phase, which is known as the post main sequence evolution of the sun. So, in the post main sequence phase, what happens is when there is not enough hydrogen fuel in the core of the sun, the nuclear reactions sort of become very slow and stops. So, there is nothing to hold the star together against gravitational collapse because the temperature falls and the pressure of the core falls, and when the star starts collapsing, gravitational energy is released, which then sort of hits up the outer layers of the sun to a very high temperature, which is sufficient to in fact enable the conversion of hydrogen to helium through fusion reactions even in the outer shell. And when this starts happening, the outer shell becomes hotter and it expands, and the luminosity of the sun increases, and when it does, it becomes a little cooler, and the radius also increases quite a bit, of course, and this is when the sun has entered the red giant phase. And in the red giant phase, the radius of the star is on the order of something like 2 astronomical unit, which is twice the present sun earth distance. So, in fact, when the sun becomes a red giant, the outer layers are going to engulf all the inner planets, including the Earth. Finally, once it reaches a red giant phase, the temperature in the core is something like 100 million degrees, and it's also quite dense, which initiates sort of another set of nuclear reactions which can fuse helium and produce higher mass elements like carbon and oxygen. And when this happens and the density of the core is pretty high, the electrons start getting very packed very tightly, and all the sort of states starts getting filled, and Pauli's exclusion principle comes into play. And so now quantum mechanical considerations become important, because at this point in time it is the electron degeneracy pressure which is holding the red giant together. Now, what this implies is that the pressure is no longer sort of determined by the equation of state, and so there is a decoupling there from the equation of state. The core gets hotter and hotter, the nuclear reaction rate starts getting faster, and eventually this leads to a runaway situation which leads to an explosion which is known as the helium flash, when a large amount of energy is released. And when this happens, the outer shell of the red giant is blasted away, and the inner part of the core collapses further, becomes very compact, and this core is typically rich in carbon and to some extent oxygen, but primarily carbon. And sort of this carbon rich core forms a different state of the star known as the white dwarf, which is held together by the electron degeneracy pressure. So, at this point in time, the nucleus starts capturing electrons, the process releases photons, which sort of lights up this expanding outer shell which has been blasted away, and this lights up the outer shell, and this sort of this combination of expanding outer shell which is being lit by this emission of photons is known as a planetary nebula, which is really the end state of the sun and a solar like system, with the white dwarf, the carbon rich white dwarf left behind in the center of this planetary nebula. And so, this is how the sun ends its life after it gets out of the main sequence, and the solar system as we know it sort of ceases to exist in some sense. We will go through some resources which are available online, so that you can brush up on some of the concepts and ideas that we discussed in this module. And so, this page, resource page, lists a couple of online resources that are available, as well as a book on stellar evolution and nucleosynthesis, which you can refer to if you want to explore this subject more. Okay, you come to the second module, which is concerned with solar activity and magnetism. So, what we will do in this module is we will briefly discuss some of the main phenomena that occurs on the sun, some of the primary phenomena which is got to do with its magnetism, and we will find out that much of solar activity actually is driven by magnetism. So, let us look at the solar structure first before we get into that, because this is not necessarily something that is observed, but this is something that is gleaned from an understanding of stellar structure, from the way balance of forces and holds together a star and how energy is transported within various layers of a sun-like star. So, the energy is produced by conversion of hydrogen to helium in the core of the sun, which occupies the inner 40% of the sun. So, beyond about 0.4 solar radius, the energy that has been generated in the interior of the sun is transported by radiation, which implies multiple absorption and re-radiation of photons by the plasma material which is in that region. And so, therefore, this region is known as the radiation zone of the sun, and the radiation zone occupies the range of radius from 0.4 solar radius to 0.7 solar radius. It sort of ends at 70% from the interior of the sun, and in this region radiation is the primary transporter of energy from the interior. So, when we hit about 0.7 solar radius, the plasma becomes opaque to radiation, and therefore, the photons are deposited in this layer, heating up the layer, and it becomes less dense and rises against gravity, and this sets up a convective motion in the outer 30% of the sun, which is known as the convection zone, where you have this hot rising plasma material which reaches the surface, radiates the heat, cools down, becomes dense and sinks down, and then gets heated up again. So, there is this big convective rolls in the convection zone of the sun, and this occupies the outer 30% of the sun. The visible surface of the sun is known as the photosphere, and is typically, when you talk of a temperature of the star, is this you are talking of the temperature of really a very thin layer near the surface, typically the photospheric level. Much of the activity dynamics that you observe is of course limited to the photosphere and layers over the photosphere, such as the chromosphere, which is the layer immediately over the photosphere and is somewhat hotter, it is about 10,000 degrees Kelvin. And then as you move up, the density falls drastically, of course, from the photosphere to the chromosphere and then to the corona. The corona is very tenuous, very thin sort of outer atmosphere of the sun. However, a very curious fact is that the temperature of the corona is typically upwards of 1,000,000 degrees, can reach up to 2,000,000 degrees in certain places, which is fairly counterintuitive, because you have the surface which is at about 6,000 degrees Kelvin, and then the heat source is sort of at the interior, but then you have the outer layers, the corona, which is much hotter. And of course, this is sort of the famous coronal heating problem, something that has kept astrophysicists troubled over a long period of time, and this is relevant not just for the sun, but other sun-like stars also, because most stars have a corona. The surface of the sun radiates at wavelengths which is close to visible. So, with the naked eye you actually can, of course, you should not look at the sun, but naked eye observations, with observation of the optical wavelength, you can image or study the sun's surface layers. When you go to the layers over the surface, for example, the chromosphere or the corona, these actually also radiate different forms of radiation which have higher energies, for example, ultraviolet, extreme ultraviolet, and in the corona X-ray radiation. So, you can use these different kinds of detectors relevant, for example, for extreme ultraviolet wavelengths or X-ray wavelengths, to image or study phenomena in the outer atmospheres of the sun, and this is typically what is done, and how we know about how the different kinds of activities that are manifest in a sun-like star. It's kind of nice to look at the history of astronomical observations a bit before we jump into the present day sun and what we know about it. And this is important because also in the historical perspective, the telescope, which was not invented by Galileo Galilei, although it is thought that he invented the telescope, formed the basis of the first solar observations, and in fact Galileo played a pioneering role in these observations. So, the story of the telescope is kind of intriguing in the sense that it was actually envisaged by spectacle makers in the Netherlands, and this is attributed to a few people like Hans Lippershey, Zacharias Janssen and Jacob Matthews, and it's thought that they actually produced the first telescope, and merchants who used ships to travel from one region to another region to sell their stuff. So, Galileo came across a version of this telescope in Venice, where one of the sea merchants bought it, and he was fairly excited and intrigued by it, and he created his own version of the telescope, and he actually demonstrated this to the public and to the Doge or the mayor of Venice, Leonardo Donato. And he also in fact sold it in the market. So, he sort of really put his stamp on the telescope, and the telescope went on to be the basis for many of his observations, sort of the scientific breakthroughs and the revolution he brought in astronomy, some of which actually landed him in trouble as well. So, what you see here is one of the drawings of Galileo from his observations of the sun, and the dark blotches that you see on the image, these dark blotches are sunspots. So, Galileo in fact was one of the first persons to observe this dark spots on the sun, although there are other people who were almost simultaneously just after him doing these observations, such as Thomas Harriot, David and Johannes Fabricius, Christoph Scheiner. He was one of the first to correctly attribute this to actual spots on the sun, which did bring some trouble for him, but we will not get into that story. But he correctly identified that these dark spots are spots on the sun, and so they are actually sunspots as opposed to clouds or something like that floating above the sun. So, following that, we have now 400 years of observations of sunspots, and in fact this is the longest running time series of any naturally observed phenomena in the universe. And what we know is that amplitude or the number of sunspots varies over time, and this variation is roughly periodic. So, the number of sunspots increases and decreases in a cyclic fashion with a mean period of about 11 years, which sort of creates a sort of a cycle of sunspots. However, the amplitude of this cycle, or the highest number of spots that is observed in a cycle, that amplitude varies from one cycle to another. The locations of sunspots are emerging on the correct latitude at which they emerge and plot them versus time, you get this very beautiful diagram which really looks like the wings of butterflies, and so this is known as the sunspot butterfly diagram. And what you see here is on the y axis there is sunspot latitude, and on the x axis there is time, and you observe that sunspots typically emerge at around 40 degrees latitude in both the hemispheres or below, and then with the progress of the sunspot cycle, more and more sunspots appear at lower and lower latitudes. Eventually, when the cycle ends, the sunspot typically appear just very close to the equator, which implies that there is a progression of the sunspots from the beginning of the cycle to the end of the cycle, and this progression is towards the equator in both the northern and the southern hemisphere, which sort of gives you an idea that the sunspot cycle is also spatially organized and structured. This was of course known for multiple centuries. However, that sunspots are strongly magnetic regions was discovered only at the turn of the 20th century, when George Ellery Hale and his collaborators in 1908 discovered that sunspots are strongly magnetized and that the magnetic fields within sunspots can exceed 1000 Gauss. So, sunspots are very large structures as well. So, typical radius of a sunspot is about 10,000 kilometers. So, in fact, you can fit in a few Earth inside a sunspot, and the magnetic field that you find in sunspots is of course then about 10,000 times stronger than the Earth's magnetic field, which is much weaker than the sun's magnetic field. On the right hand side, we have a current day observation of the sunspot. And in this observation, you also see much more fine structure. For example, the inner part of the sunspot, which is very dark, is known as umbra, and the outer parts, which you have these fibril-like structures which are elongated, is known as the penumbra. And in very high resolution telescopic images, you can also see the convection and the convective granules in the surface layers, which is visible right here outside of the sunspot structure. You see this kind of sort of convective granules. When you look at the activity of the sun in various wavelengths, for example, if you want to image what is going on outside the sun's surface, ideally you would be using different wavelengths, for example, ultraviolet or extreme ultraviolet, which is what is portrayed sort of here. And then you start seeing the plasma material that is emitting at this higher energy radiation. What you see here is one of these phenomena where you see these plumes of plasma which are being ejected away from the near surface layers into the chromosphere and higher up. So, this is something that is over the photospheric layer, and this dynamics is happening in the chromospheric layer, and it sort of shows that there is a mass loading of plasma from the near surface layers to the higher layers, And this eventually sort of forms the basis of outflow of solar plasma known as the solar wind, which permeates the solar system and extends to the end of the heliosphere. Sort of defines the sphere of influence of the sun, and this heliosphere is then full of solar wind particles, which are essentially solar plasma containing elements, atoms which have been produced in the sun and which are being carried away throughout the solar system. So, most stars which have a hot corona also have a solar wind. These sunspot structures are also the seats of solar magnetic storms. So, these storms are one of the most dynamically important and one of the most energetic phenomena in the solar system. In fact, they are the most energetic phenomena in the solar system, because each of these storms can carry energy which is on the order of 10 to the power 24 joules, which is on the order of 1,000 billion atomic explosions at one instant in time. That is the amount of energy that these storms can have, and they typically sort of eject a vast amount of solar material from the sun's outer atmosphere into outer space at very large speeds, which can exceed a few thousand kilometers per second. And these storms are something that create severe space weather. The sun's corona, which is the outermost layer of the sun, is very thin and very tenuous, and therefore the flux of photons that you get from there is very low, and you normally do not see it because your eyes or detectors are saturated by the emission from the solar disk. But a total solar eclipse provides a fantastic opportunity to actually view the sun's corona and to image it. So, the image that you see here, for example, is from the solar eclipse of 2017, I believe, where the moon has completely obstructed the sun's disk, and you see the outer layer of the corona, which is suddenly visible because your eyes are not being saturated, or the camera is not being saturated by the photons from the solar disk. Now, what is surprising here is you see that there is a lot of fine structure in the corona, and it turns out that that fine structure is actually due to the magnetic structuring of the corona. It's the magnetic fields which is responsible for the coronal structuring and for much of its emission. In fact, it's the magnetic field which is also responsible for very high temperature of the corona. The million degree solar corona is thought to be due to magnetic reconnection, which sustains the kind of energy release that can heat up the plasma to 1,000,000 degrees. And once you do that, you of course then have emission in very high energy radiation, such as X-rays, and so you can actually view the corona in X-rays, not from the earth of course, but from outer space. So, what you see here in this image here from the Yokowo satellite of the Japanese Space Agency, where you see the full solar corona, the X-ray emission from the solar corona, and you also see the X-ray emission is also highly structured. And in fact, we know that this structuring is because of the association of this emission with sunspots, and it is the overlying magnetic loops of sunspots which are emitting this X-rays and which sort of form the backbone of the sun's corona. Okay. So, with that brief description of some of the main activities of the sun, we will briefly summarize some of the outstanding challenges in solar physics, which are sort of driving the research at this point in time, before we pick up a few of those topics and look at them in greater detail. So, for example, one of the big questions of course is, and this is not just in the context of the sun, but also of solar stellar magnetic fields, is how are magnetic fields produced in the interior of stars. And specifically in the solar context, we are now asking the question, is it possible to predict the future activity of the sun? What do you mean here by this is whether you can predict the amplitude of future sunspot cycles. This is being done now. We are trying to figure out how far in advance you can make these predictions. We are also trying to understand what is the structure of plasma flows in the sun's interior, and to do this we use a technique known as helioseismology, which looks at oscillations in the sun's surface to map out the wave travel times of acoustic waves based on inversions, how flows sort of impact this travel times, one can constrain the plasma flows themselves in the interior, and this is an exciting field which is important also for models of for the generation of the solar cycle, because these plasma flows drive magnetic dynamo that is at the heart of the origin of solar magnetism. We are also interested in knowing why the sun's corona is so hot and why is it so structured, and what is the role of magnetic fields and Alfvén webs in maintaining and heating the sun's corona. Also interested in knowing whether solar flares and solar coronal mass ejections, which are the most violent of solar storms, can be understood and predicted in advance. Some of the most challenging and controversial questions in the context of Sun-Earth system is how has the sun's output varied in the past, and how has this influenced climate change? And the answer to this question is very important, because this allows you to separate out the natural and anthropogenic causes of climate change. And finally, one of the directions in which this field is rapidly developing into is known as star-planet interactions. And in this domain, what we are interested in is in finding out how does the activity of stars like the sun and its evolution over long time scales determine the evolution of planets and their atmosphere, and therefore their habitability. And this is a question that is not just relevant for the solar system, but this question is also relevant for other systems like exoplanetary systems and for the search of extraterrestrial life beyond the solar system. So, what we will do now is we will end with a film which sort of brings together all these different levels of solar activity together into a nice movie. Okay, so and here is some resources on the sun. So I have a couple of online resources. One is a Wikipedia entry, which is a general sort of, it provides very general basic information on various aspects of the sun and solar activity, its structure and properties, which is a good sort of first place to start, getting a understanding of the physical properties of the sun and an idea of what kind of activity it hosts. And if you want to look at very recent, almost real-time observations of the sun in various wavelengths, starting from the sun's surface to its outer corona, you can look at this website known as the solarmonitor.org, where they collect pretty much very recent observations from various satellites and ground-based observatories. And finally, this book called the Cambridge Encyclopedia of the Sun by Kenneth R. Lang is also a very nice sort of first book, which is written in simple terms, which has some nice pictures, images and simple explanations of various solar phenomena, and is a good first book, understand the sun at a very phenomenological kind of level.